Hello, everyone. Susan Nash, AAPG. Really happy to be here today and really excited to have our wonderful AAPG Academy presenter today, Molly Turko, who will be talking about structural geology that you need to know in the energy transition. And I'd also like to just make a few announcements. Please look at the chat and you will see that you have a link there if you scroll up in the chat. And it's to purchase the extended package for $35. You'll get CEUs and professional development hours, plus wonderful articles that Molly has sourced for us. And she sent me quite a few, even one more today. So I'll be creating a website and we'll be sending a link so you'll have access to that shortly thereafter. And for all of you who are members, thank you. I'd like you to encourage you to go ahead and rejoin or pay your dues or renew. And if you, and I'd also like to encourage you to tell people about the benefits of AAPG, where you get access to these types of free webinars, also all kinds of opportunities to present and be a part and build your career and diversify. So it's just really a great thing. And also you have the opportunity to be a part of the division, which is Molly Turko is now, I guess, vice president or is it president-elect, right? Vice president?
Vice president.
Yes, vice president, soon to be president, I believe, of the petroleum structure and geomechanics division. So we're really thrilled that she's in that position. And she's also involved in the sections. I think she's agreed to be help be a host or a chair for upcoming mid-continent section annual or meeting. And Linda Sternbach is here. If she'd like to talk a few minutes, that would be fantastic.
Great, hello. Well, thank you, Susan. I'm really looking forward to this talk, Molly. I've been excited all day. I want to see your talk. Just mentioned on AAPG, I'm the vice president of sections, and I just want to, if you're interested in news on the SPE AAPG merger in the chat, you can see our website link to see what's going on. And also tonight at 8 p.m., if you check your email, AAPG sent out a Zoom link. There'll be an open town hall forum, 8 p.m. Central Standard Time. I can't send you the link. It's in an email. Look for AAPG email to you, and then you'll learn more about what's going on.
Thank you, Linda. Well, I think that's all we have for now. So I just really am thrilled to encourage and invite Molly to share her screen. I'll stop sharing mine, and to start our AAPG Academy webinar.
Awesome. And all right, let me figure out where to throw this little box. Hopefully, awesome, good to know. And hopefully you can see my little laser pointer there in the background. Well, welcome everybody. It's an honor to be here today. I am going to be talking about structural geology you need to know in the energy transition. And just a little bit about myself. I received a PhD from the University of Oklahoma, where I studied under Dr. Shankar Mitra, who's very well known in the structural geology world. I also went to the University of Tulsa. That's kind of my hometown, that area. And I have quite a bit of experience in the oil and gas industry. I've worked for a structural geologist for several companies in Tulsa and Oklahoma City. I've done a lot of fracture studies and seismic interpretation. I love to do modeling when it comes to faults and fractures, as well as tectonic studies. I'm also an industry consultant for myself. I have my own little LLC, Turko Tectonic and Structural Geology, but I also do consulting with Applied Stratigraphic, and we do a lot with the mining industry as well as oil and gas. I teach several in-house and online structural geology courses, both mining and oil and gas focused courses. And one of my favorite things to do is to run field courses in Nevada as well as Oklahoma and Arkansas. And here's a fun picture from the Valley of Fire. It's just east of Las Vegas. It's a beautiful place to see fractures and faults and all kinds of great things, structural geology in the field. So for today, we're gonna start by talking about critical minerals. That's a bulk part of this talk. And then we're gonna talk a little bit about carbon capture and then geothermal. And I have my first disclaimer of many. This talk will consist a lot about the geology information. You know, if you go to YouTube and you look up critical minerals, you'll get a lot of talks that discuss the economics. And while that stuff is very important, I do want to be very focused on the geology for this side. So we'll start with critical minerals and talk about what they are, and then we'll get into these other two subjects below as well. And here is my second disclaimer of the day. I can't teach you everything you need to know in 1 hour, but I can tell you what you need to know, at least from my own perspective. Others might want to tell you more or less, but I do hope to maybe teach you a few concepts in the process. So get your notepad out, start taking some notes, and then hopefully I can teach you a few things. So let's start by talking about structural geology of critical minerals. And we're going to kind of break this down into two parts. We're going to talk about the exploration phase versus the development phase. But first, what are critical minerals? Well, I really like this definition from the Australian government. Critical minerals are metals and non-metals that are considered vital for the economic well-being of the world's major and emerging economies, yet whose supply may be at risk due to geological scarcity, geopolitical issues, trade policy, or other factors. And the USGS has a great interactive map database. If you buy into the package, I have all these links so you can just click on them. But this is a great place to go to kind of see things visually. You can turn layers off and on of this big list of critical minerals down here, and then kind of zoom in and see where those are mined and learn a little bit more about those. Now, why are they needed? Well, critical minerals go into a lot of industry and technology, as well as batteries. Battery is a big one now. So this chart is very simplified, but you can see a couple of the critical minerals listed below. And then if you're able to go to this interactive map, you can kind of click on that and see where that's mined around the world and learn a little bit more about that country or the geology of that country. So let's talk about critical minerals in regards to structural geology. And like I said, we're going to break this down into the exploration phase versus the development phase. So when I refer to the development phase, I'm kind of thinking along the terms of there's already a mine that's there, and now you're trying to figure out where to go next. Do you want to go east? Do you want to go north? Or do you want to go deeper in the system? But when I'm talking about the exploration phase, that's more thinking about in terms of where's the next big mine? Where should we focus? And there's a whole list of topics to kind of go through. So let's start with the mineral systems approach. So if you're working in the oil and gas industry, the mineral systems approach is very similar to our petroleum system elements. So you want to think about things like your source, your reservoir, your trap, your seal and migration. But in terms of the mineral industry, this mineral system approach, it actually considers the origin of the deposits in the framework of lithospheric scale processes from the time-honored perspective of source, fluids, transport, and traps. And if you Google the mineral systems approach, you'll see lots of charts listed like this. And I could be wrong here, but I feel like this is a relatively new approach. It's an applied exploration strategy that allows for more predictive models. So previously, like historically, in the mining industry, they might look at more pattern matching of various ore deposit types, which we'll look at some different types next. But in this case, you will use knowledge of the underlying geological processes and the tectonic setting to identify prospectivity. So if we look at this chart here, it's kind of divided up between the process and the scale. So we go from the district scale, so that might be something like a big basin. And then you can go down to your camp scale, which might represent an oil or a gas field. And in the prospect scale, and that might be where you drill your well, but in this case, that's more looking at where you would put your mine. So starting with the big scale, big picture, you're definitely going to need some type of source. So a lot of times your fluid or your metal source comes from the magma. So here on these charts, I've kind of just labeled where your source might be. Then you're also going to want to think about the geodynamics. So what type of orogenic event is setting the stage for this? So in this case up here, you're looking at a collision between continents and ocean crust. That's creating some structure over here to the right. So looking at B, where I've labeled B, this would essentially represent your crustal scale faults that are linking down to your source. And then when we look at C, now we're more looking at the architecture. So you want to think about the type of faulting. And in this case, you're looking at a oblique convergence. So your type of faulting might represent large scale strikes of faults. And then once you kind of start to take that down to the prospect scale, now you're really going to want to pay attention to the geometry of those faults, and do those geometries allow for you to put a prospect there? Is that an area where you might expect veins or some type of fluid to rise and essentially be deposited there? And then lastly, this kind of gets into the trap of the deposit, and this gets a little bit more complex, but I felt like this diagram kind of did a nice job of showing some of these relatively near surface processes to kind of describe what might cause a trap or a deposit. So in the mining industry, when we use the word trap, we're thinking about some type of process. So maybe it's a decrease in pressure, and that can allow metals within a hydrothermal fluid to drop out into, say, veins or very large fractures. And that would essentially represent our prospect. So as I kind of mentioned this before, this is a relatively new approach. It's kind of big picture, zooming down into small scale. But historically, geologists have studied various ore deposit types, and this removes some of the complexity associated with each type. But what exactly is an ore deposit type? Well, an ore deposit consists of one or more bodies, and an ore body is a massive rock that contains ore from which a commodity of value will be extracted. Ore deposits can be grouped several different ways. One of the very common ways is temperature. So you'll hear terms like an epithermal deposit or a mesothermal deposit. And this is simply referring to the temperature at which those deposits formed. And in reference to the ore deposit type, you have several listed over here on the right. So maybe you've heard of kimberlite dikes and diamonds, or copper porphyries, or things like epithermal deposits. Even placer deposits are listed over here. So these charts, this terminology and lingo, it may take some time to get used to it, because at first it's very overwhelming because there's lots of different ore deposit types, and trying to learn the geology of each one can become a little bit overwhelming. So my recommendation is to maybe just pick a few of these and then dig into those, and that can kind of help familiarize you with lingo and terminology. And you want to think about what's controlling the deposit. Is it structure, or is it more chemistry or matrix hosted, which we'll look at some of that. Ore deposit types, they can also be grouped by material transport. So in this case, you're looking at things like a magmatic ore versus hydrothermal ore deposits. But one of my favorite charts is this one here on the right. And I like this as a structural geologist because it's being grouped by the tectonic setting. So even just as a geologist alone, this chart makes a lot of sense. So down here where you see magmatic ore deposits, you'll be looking for the A, this red circle in the A, and this can show you places where you can get those magmatic ore deposits. Or hydrothermal deposits here in blue, and even surface related deposits here in this kind of orange color. And then the type of charts or the type of ore deposit is being shown down here. So if you're trying to figure out what's the tectonic setting for copper porphyry deposits, or what about these volcanic massive sulfide deposits, coming back to this tectonic setting chart is going to be very helpful. And this is something that you'll get if you buy into that package. It's one of those papers I submitted. So another great reference are these YouTube videos by Andrew Jackson, Ore Deposits 101. These are great to just get some snacks ready and click on YouTube and start to watch some of these. I definitely recommend this one, the introduction. And then as you'll see from the rest of these, they have the type of deposits that he goes over below each of those. So it's really a great reference to kind of get you started. At one point in time, I had watched all his videos and really enjoyed them. So I do kind of want to just put that out there as an option to really kind of familiarize yourself with different ore deposit types. Next, I really want to emphasize the importance of the tectonic history. This is really going to be true for the oil and gas industry as well. But never underestimate the importance of the tectonic history. And you really can't go back far enough. So you want to consider what is the timing of deformation that has happened in that area versus the timing of your ore deposits. Have there been multiple deformation events? And I would really recommend constructing some type of tectonic events charts. And this is just a generic one that I threw out there. So you can see that I put things on there like continental rifting and magnetism. You had an ore deposit and then a later fold and thrust belt. These can be really helpful for trying to figure out the timing, which is true even for the oil and gas industry. You want to know the timing of your oil generation versus the formation of your traps and your seal. And I do have one quick case study to kind of emphasize this. This is from the Southern Canadian Rockies. And this area was impacted by late Proterozoic rift faults. These rift faults can be seen in magnetic data. So learning some very simple interpretation techniques of gravity and magnetic data can also be very helpful. But then later, as I mentioned, we had a fold and thrust belt to override this area. Now where you see the yellow as well as these stars, that represents ore deposits within this area. And what you'll find is that a lot of these ore deposits actually line up with these paleo rift faults. So understanding the tectonic history is really important for understanding where your your ore deposits could have occurred. So if you simply looked at your fold and thrust belt, you may have missed that large impact of the earlier structures on those mineral deposits. Because those faults, those are our pre-existing basement faults that link down to our source. I want to touch a little bit on kinematics. Kinematic is a very important word for structural geology. And it's basically the branch of mechanics concerned with the motion of an object. So for structural geology, kinematics is the description of the path that rocks took during deformation. So if we look down here at our little T-Rex, we can put a fault through him, basically translate him. We can simply shear him or rotate him or even dilate him. So the kinematics is how we would describe that path. So here's a nice tile that I found with a nice little shear zone. So we've had some distortion here. And then these are some faults right outside of Moab. So you can see we've had a nice fault cutting through here. And even though kinematics describes the path, the other second part of this definition is you want to understand this with references to the forces which cause the motion. Well, in structural geology, that's simply our stresses. So let's talk about stress. And when we talk about stress, we're going to refer to something that's called our stress regimes. And stress regimes describe the type of faulting that you would expect if the stresses are high enough to break the rock. So very commonly, we would consider normal faulting, reverse faulting, and strike subfaulting. And stress regimes, they are defined by 3 magnitudes and 3 directions. So if you think about this nice cube of rock, you have 3 stress directions. You have a vertical and then 2 horizontal. And each of these stresses has a magnitude. So the one with the greatest magnitude or maximum, we would call that S1. And the one with the minimum, we would call that our S3. But really, it's going to be the magnitude of these vectors that determines the stress regime. So when our vertical stress is highest, we would call that a normal faulting regime. So if those stresses are high enough to break the rock, we would expect normal faulting. So up here in this little diagram, you can see our nice normal faults. But what you also see posted on there are our stresses. So this little symbol up here, that's our stress, that's our sigma. So sometimes it's called sigma or S1. And you can see that S1 is vertical. Here you can see S3, our minimum. So as that's pushing down, it opens in the direction of our minimum, which essentially makes our fault run parallel to S2. And something that's very common in nature is the orientation at which that fault forms. It almost always wants to form close to 30 degrees to S1. So if you think about the orientation between this vertical stress and the angle of that fault, that's going to be 30 degrees. Now, geologists, we like to measure things from horizontal. So if we go over here, that essentially represents a 60-degree dipping fault, assuming that formed when bedding was horizontal. In terms of reverse faults, our S1 is horizontal. So when you measure the angle of this fault to your horizontal, that's 30 degrees. So once again, we see that 30-degree angle. And then taking that over to strike slip faults, once again, S1 is horizontal, and the orientation at which our faults want to form are 30 degrees to S1. But of course, if we measure that to horizontal, that would essentially represent a vertical fault, which is very common for strike slip faulting. So understanding the relationships between your stresses, the orientation and the magnitudes, and the type of faulting that you can expect to develop, we would all kind of classify that as kinematic relationships. And all of that can be very important for understanding the type of faulting to expect, or if you're thinking in terms of paleo stresses, what type of faults formed in the past. And then the other really important thing is understanding fracture mechanics. So fractures can go by many names. You can call them joints, you can call them veins, you can call them fissures, you can call them a lot of different things. But one of the things you'll want to understand is the fracture classification. So we have mode 1. That would essentially represent our opening mode fractures. So things like veins, joints. Then we also have mode 2, and that would represent our shear fractures that are sliding past each other. Or if it's a much larger scale, we might call that a fault. So mode 1, that can go by many different names. Mode 2, typically that's considered a shear fracture or a fault. And these other two are pretty much hybrids of mode 1 and mode 2, more or less. And if I bring back this block diagram, this represents a normal faulting regime. You can see our S1 up here is vertical. You can see that nice 30-degree angle on our faults. These would essentially represent our shear fractures. And then our tension fractures, or our mode 1 fractures, are going to be vertical. And the orientation at which they form is pretty much going to be parallel to S2. So understanding the relationships between fracturing and stresses is also going to be very important for predicting trends of fracturing and trends of faulting. Now, what causes a rock to break? A lot of that is going to be related to concepts of brittleness or ductility. So strength is the amount of pressure needed to break a rock. So I mentioned these stress magnitudes. You have 1, 2, and 3. Once that stress 3 is greater than the strength of the rock, that rock is going to want to break. But brittleness, that refers to how much a rock will deform before it fails or before it breaks. Sometimes we think about that in terms of strain. So strength is essentially going to be an internal rock property, whereas brittleness, we think about it more about a behavior. But there are many factors that can impact brittleness, both external and internal. That can include things like your pressures acting on the rock, stress differentials, even things like temperature and strain rate. So how fast does that rock deform? All of that can really determine if a rock wants to behave more brittle or more ductile. Your internal things include the mineralogy or the lithology of the rock. Sometimes we refer to that as the mechanical stratigraphy, especially if we're thinking about sedimentary rocks that are stratified. But even things like grain size and porosity, or even pre-existing weaknesses, can all determine how a rock might behave. So I kind of like this little diagram here. So we have a granite. That granite is behaving a little bit more brittle. And then as we move to the right, we have things like shale and salt, and these are behaving a little bit more ductile. And the key thing to remember is that all of these are acting at the same temperature and pressure conditions. But the key thing here is that it's the mineralogy of each of these that is really impacting the brittleness of those behaviors. So fracture mechanics is going to be very important. That's a whole hour or 3 hour or even a week-long course to learn all about that, but it's something that you will definitely want to know if you're going to be in the mineral exploration industry, even some of these others that I'll get to eventually. So that covers a few key topics of the exploration phase. Next, I want to talk about the development phase. So as I mentioned, in this case, you're thinking about, you have an existing mine and you're developing it. Where do you want to go next? Do you want to go deeper or laterally? Things like that. And in order to really answer that question, you really need to think about, is the deposit structurally controlled? Is structure controlling this deposit, or is it something else? And I'm not sure the best word to use, but I'm going to say, is it matrix controlled? And we'll kind of see what that means. So if it's structurally controlled, you'll need to understand orientations of veins, faults, or fold. So we'll talk about how to read and gather this information. And then you also want to think about, what is the control on the orientations? Is it simply regional stresses or something that's a little bit more local? Or are we looking at things like fault geometries or hydraulic fractures, which we'll look at? And if it's not structurally controlled, maybe we'll think more about the matrix of the rock. And in that case, you will want to consider things like chemical alterations in those geometries. So if it is a structurally controlled deposit, something that's going to be really important to think about is your rock fabrics, and you're going to want to have a good understanding at recognizing rock fabrics. So I like this chart here on the right. This is great for kind of defining some of the more common brittle fabrics versus more common ductile fabrics. And this puts some nice labels on what we see. And just to break it down into essentially two, whenever we see a fault, and then we see our secondary structures, a very common secondary structure in nature are these little Rydell shears. Notice how this Rydell shear is subparallel to this main fault zone here. Well, if I simply break it down into a fault and in the Rydell shears, what you'll notice is that these Rydell shears, they kind of make little arrows. And those arrows are pointing in the direction of slip. So in this case, you're looking at something that's pointing to the right. So this would be a little right lateral strike slip fault if you're looking at that in map view. And then this picture is it's a little bit small to see, but what you'll see are some more through-going faults or shears. And then secondary to that are these little Rydells. And those are indicating that this fault system here has reverse slip. And that's a really great indicator for brittle deformation. The opposite is kind of true for ductile. Notice a lot of these shapes that you see are very sigmoidal. You see a lot of S shapes. But if we simply break it back down into a through-going shear zone and the little sigmoidal shapes that follow that, now what you'll notice is that these little sigmoidal shapes are pointing in the opposite direction. So if those were to make little tiny arrows, those point in the opposite direction of slip. It's still a right lateral fault or a right lateral shear zone, but these are pointing in the opposite direction. So being able to recognize those in the field can be really important for trying to think about your slip sense. Are you looking at normal faults or reverse faults? And whenever you're in some type of homogeneous igneous rock like a granite, it can be really hard to figure offset because you don't have that bedding to help you. But these fabrics can be very important because they actually tell you a lot about relative temperature and pressure conditions during deformation. So I like this chart because here you're seeing depth as it gets deeper. And then over here, this is kind of representing more brittle deformation, a transition zone, and ductile. Notice those little sigmoidal S shapes that are shown down here. And if I kind of edit this diagram, I went ahead and drew in our brittle Rydell shears up here. But this is really nice because this also has a permeability curve with it. So what you'll notice is that as you are more shallow towards the surface in an area where you can have brittle deformation, you'll see that you have relatively higher permeability in systems. But as you get deeper, sometimes you have less permeability within those more ductile behaviors. And then this is just telling you some of the more common metamorphic facies like blue schist and green schist, and then some generic fracture patterns. So recognizing brittle versus ductile behavior, that can tell you your kinematic slip direction, which can be really helpful with those orientations and understanding paleostresses. And then it can also sometimes be really helpful with understanding timing of deformation. If you recognize a brittle behavior, maybe that is telling you that that deformed near the surface, relatively shallow, relatively cool, versus if you see a more ductile behavior, that might tell you something that formed deeper under higher temperature or pressure conditions. And if you remember, a lot of our ore deposit types are classified based on temperature. So something like epithermal would be a little bit more shallow, or mesothermal would be more deeper. Okay, hopefully that's not too much at once. So another really helpful tool for understanding orientations of structures such as faults, veins, and folds is going to be the stereo nets, those dreaded stereo nets. If you're a geologist and you took structural geology as an undergrad, it's possible you hated stereo nets. But I'm not going to get into the details of this. There are some great YouTube videos out there. You can do some Google searches and really understand how to read a stereo net, how to plot data on there. But these can be very important because sometimes in these deposits, you will have multiple vein sets, multiple fault sets. Some of those occurred simultaneously. Some are older, some are younger. The stereo nets and plotting this information can be very helpful for determining those sets. So structural geology, you need to know if you're working a developing mine, you want to go ahead and get familiar with your stereo nets and rose diagrams, these types of diagrams down here. And then you also want to determine the control on those orientations. So are we looking at something like regional fracture sets where our regional stresses are controlling the orientation of regional vein sets or fracture sets and faults? Or is it more about understanding the geometries of the faults? So the geometry of the fault, that can cause for areas to be under tension versus compression. So that can cause greater amounts of fracturing or lesser amounts of fracturing, depending on fault geometries, whether it's bending or you're stepping. Or are your fractures related to some type of hydraulic process? So that would represent this diagram over here. As you get this magmatic body intruding and working its way up towards the surface, it becomes overpressurized and there's fluids in there. And there becomes a point where it essentially naturally hydraulically fractures itself. That can cause some really chaotic fracture properties. But those are going to be very important because those still make up your vein systems, whereas your hydrothermal fluids move up through there, they can fall out of solution and those veins can then represent your ore deposit. So what if it's not a structurally controlled deposit? And I kind of just threw this word out there. What if it's more matrix controlled? And what do I mean by that? Well, in this case, your ore deposit may be concentrated due to some type of chemical alteration. This is common for porphyry deposits. So if you look at this map view, you can see those colors on here. Those colors just represent the different compositions of the rock. And some of those compositions are going to have a higher concentration of a metal like gold, and some of them are going to be less concentrated. So if that's the case, you're really going to want to work closely with your igneous petrologist or a geochemist. And that way you're trying to figure out what's the composition of the matrix or the wall rock versus trying to chase those veins. And sometimes this is very commonly called an alteration halo. And this would be a very simplified cross-section view. So as this igneous body progresses towards the surface, there are zones of alteration in here. And some of those zones, this one, for example, they're showing that as the ore zone. This is where you would have the higher concentration of that metal. Now, I would argue that in most of the cases, it's typically going to be both. So why would I say that? Well, if you think about igneous rocks, they're very, very impermeable. So how do you get hydrothermal fluids to flow through very impermeable rock? Well, you want that rock to become fractured. Let's go back to this diagram. So this is going to be the case here. So as you have some type of overpressured body with hydrothermal fluids, eventually that's going to naturally hydraulically frac itself, which causes all these fractures to propagate up towards the surface. Those fractures then become pathways for those fluids which are causing the alteration. So structural geology is still king, even in these matrix controlled deposits. And just for a quick case study, this is from Cripple Creek, a very well-known area in Colorado. But on the surface map, you can see the different patterns showing the different composition of the rock in the background. But what happens is that you have pre-existing faults and fractures. Those act as mechanical weaknesses. So as you get enhanced fracturing going through those, that actually makes a pathway where those hydrothermal fluids want to flow. So if you look at the rock from here, what you can see is that it's incredibly fractured. Where you see that kind of brown color, that's the oxidation. And these areas where you get these veins or these dikes, this is where you get your best grade of ore. In some of these areas, you get approximately 10 grams per ton of gold in the veins and the dikes. But once you move away from that, you get this disseminated gold concentration in the matrix. And there you're getting less than a gram of ton in that wall rock. That's sometimes called a wall rock versus your veins or your dikes where you're getting that higher concentration. So this is a case where we do see a lot of that alteration, but where that alteration is, that is highly controlled by the veins and the dikes within the system. And as this section comes to a close, I want to recommend a great book from SEG, the Society of Economic Geologists. It's not exactly a textbook, but it does have a lot of great papers in here. And it's one that I enjoy. There's some great case studies, some great figures and images. They really break down the geology of these different deposits in here. And it's one that I just wanted to throw out there. I did snag a few images in my talk from this book as well. So definitely look into getting this one if you are wanting to get into exploring for critical minerals and learning all about those from a structural geology standpoint. So for the next part of the talk, I want to get into carbon capture, and I will discuss why we don't really like the faults and the fractures. I'll also touch on induced seismicity, and then I'll end with a little bit on geothermal. So what is CCUS? Well, it typically stands for carbon capture, utilization, and storage. And basically what you're doing is you're capturing the CO2 from your production and you're putting it back into the subsurface or utilizing it elsewhere. So why would we not like faults and fractures? Well, we don't like them because it's possible that they can cause our CO2 to leak back into the surface, and that would essentially defeat the purpose. As long as they don't do that, then we don't mind having a few fractures in our reservoir. But many of the concepts related to carbon capture, these overlap very heavily with the oil and gas industry, as well as many of the concepts that you can learn in the mining industry as well. So we're going to touch on a few of these. We'll talk about mechanical stratigraphy. That's something that you're going to want to understand. We'll also talk about seal and fault seal integrity, as well as fault geometries, which includes things like fault damage zone, the shape of the fault. Fracture studies can be very important. You really want to understand if those fractures in your reservoir are acting as permeable conduits, or maybe they're all highly mineralized and they're not acting as conduits. Proper seismic interpretation is going to be very important, especially if your carbon capture reservoir is in maybe a structurally complex area. And I have this motto that I love. It's every good geophysicist needs a good structural geologist, but then every good structural geologist needs a good geophysicist. You know, I don't want to go around and start interpreting seismic artifacts as faults. So we kind of go hand in hand. And a lot of the topics related to CCUS, they're very easy to transition from the oil and gas because they include our petroleum system elements like migration, seal, trap, and reservoir, especially fractured reservoirs. And there's one that I didn't have on this list. I don't know if anybody caught that. That would be our source. So for CCS, we're not necessarily looking for an organic rich shale or some type of source rock. Let's start by quickly talking about mechanical stratigraphy. So mechanical stratigraphy, that represents the mechanical properties of the rock, the thickness of those mechanical properties, or those mechanical layers, and the frictional properties at those boundaries. So a lot of this is going to be based on concepts of brittleness and ductility, and it's going to be highly impacted by mineralogy, depositional texture, porosity, and competence. And as we saw earlier, mechanical stratigraphy and brittleness or ductility, that is going to be a result of functions that are both internal and external. I like this diagram from David Farrell et al. But here you're looking at chalks versus marl. Nice little stratigraphic section here on the right. And on the left, you're looking at the Smith profile. So kind of just think about this as a proxy for rock strength or rock hardness. And this profile does a nice job essentially breaking down some of those mechanical units. You can see some are very hard versus some that are very soft. And it's a nice way visually to kind of just see mechanically those geomechanical changes throughout that stratigraphic section. And then this is a nice chart from Stearns and Friedman. It's kind of a classic, but here they're looking at fracture intensity versus lithology. So things like a quartzite or a chert are going to be very brittle. That might contain a lot of fractures. And then if you move to the right side, something like a limestone might behave a little bit more ductile. And my guess, they don't have shale on here or mud rock, but my guess is a shale or a mud rock would show even less fracturing. You want to make sure you understand some concepts related to fault geometries. So sometimes if a fault bends a certain way, that can cause for areas of tension versus contraction. So if you're looking at this in map view, an outside bend, that would create a little zone of tension. There's kind of an old rule of thumb that rocks are weaker in tension, stronger in contraction. So if you have this outside bend, that might be an area of enhanced fracturing. And the same goes for your cross-section view. And then once again, considering the mechanical stratigraphy and how that might change the geometry of the fault as well. So both of these are going to be very important concepts. Now let's talk about another very important concept, and that's induced seismicity. So there are some concerns that with carbon capture, that might lead to more induced seismicity. Well, if you're injecting the CO2 back into the ground, that can change your pore pressure conditions. So there are some concerns that might lead to small earthquakes. So that might be a good concept to know about, although there are some authors who have argued that the risk might not be as bad as we think it's going to be. But regardless, if you are thinking about structural geology, you need to know you're going to want to understand some concepts of critically stressed faults. So a critically stressed fault or fracture, those are faults and fractures that are under optimal condition for shear failure, reactivation, earthquakes. So the three big things are going to be the orientation to stress, the pore pressure conditions, and the coefficient of friction. So I'm not going to get into the details of each of these, but you're going to want to understand concepts of your friend, the Moore-Coulomb circle. So hopefully this doesn't bring back nightmares of structural geology in undergrad. But the Moore-Coulomb circle is a great way to really understand these relationships and how they might change under changing pressure conditions. So lastly, I want to quickly touch on geothermal and notice that for faulted and fractured reservoirs, I put this smiley face because in geothermal, we tend to like them. Well, let's talk about what geothermal is. So in this case, we are using the Earth's natural source of heat by injecting water into a geothermally hot reservoir, which then produces a steam that then can generate electricity. Once this steam cools, it is then pumped back down. So it really is a cycle of water, and that helps to generate electricity. And this is one of my favorite types of energy sources. I feel like it really is renewable in a lot of ways. The only downside is sometimes you are limited geographically. So in order to find these hot rocks at a good depth, you might be limited geographically. But the other thing that you need to have is you need to have enough permeability to cycle this water through before the energy is lost in the process. What can enhance permeability? Well, faults and natural fractures can. So here's a case where they're injecting the cool water in. It's finding those natural fracture pathways. That's a good, quick way to get water through that hot system and then back to the surface to generate that electricity. And in some cases, you can even frack a reservoir and create some hydraulic fractures to help out with that system. So we like fractures and faults. Why do we like them? Because they enhance permeability. How do we like them? We like them critically stressed. So we just talked about what critically stressed means. And some studies have shown that critically stressed or critically oriented fractures can actually remain open in the subsurface while others remain closed. However, another disclaimer, you have to consider the impact of mineralization and just fracture complexities in general. This is why fracture studies can be so important. But basically, if a fracture is critically stressed, that means that it could be staying propped open, or a slight amount of shear or reactivation can actually cause a fracture plane to open. So this is a great paper, and it's one that I give you to download. But this is basically saying that those fractures that are oriented and such that they experience a high ratio of shear to normal stress, that these are more likely to flow, and that these critically stressed fractures are in a state of stress that is close to failure. So we would call that a critically stressed fracture. And that this significantly can increase the permeability of that. So here on these rose diagrams, this is a rose diagram showing the orientation of all the fractures in a reservoir. And then here on the right side, this is showing fractures from transmissive zones only. So what we can see is the maximum horizontal stress is oriented a little bit northwest, southeast. And in all the fractures that are within plus or minus 30 degrees from that, those show up as being the transmissive fractures. If I take this block diagram here on the left and kind of just orient that with this rose diagram, we can see that 30-degree angle. That's a great angle that really, faults really love to form at that 30-degree angle, faults or shear fractures. And then of course, the mode 1, the extensional, those tensional joints or veins, those form perpendicular to that. So we like our fractures and faults to be critically stressed if we want that enhanced permeability. And then here's just another example from the Dixie Valley geothermal area. This is a fault-controlled geothermal system and is the hottest known deep circulation system in the basin and range. So here's some nice cross sections. You can see some faults and several wells that were drilled into this fault system. And if you really start to read into this, what you'll see is that there are wells that they called producing wells, In other words, good wells, good producing wells, and non-producing wells, wells that didn't quite meet that circulation need. And when you look at the Rose diagram of some of these mapped fracture and fault trends, what you'll see is that where you had the production wells, that's where you had your faults and your fractures that could be classified as critically stressed or optimally oriented. And where you had those faults and fractures that were slightly deviated, those are the ones that they typically classified as non-producing wells. So when it comes to geothermal, it's going to be really important to understand concept of critically stressed faults and fractures. You're also going to want to understand fault kinematics as well as mechanical stratigraphy, especially if your fractures are those permeability pathways. You really understand which lithological units are more likely to be highly fractured. So as I mentioned, in the good wells, the fractures were more aligned with SH max and at those critical orientations. So to summarize, when we think about exploration for critical minerals, it's going to be good to familiarize yourself with that mineral systems approach and the various ore deposit types. Remember your tectonic history, because sometimes when you have multiple tectonic events, you know, something that happened in the past really could have set up a great migration pathway for crustal faults, the fluids, for something that happened later. Once you get into the development phase, in terms of structural geology, it's going to be very hands-on. You're going to be doing lots of mapping, whether you're in a mine or at the surface. So recognizing those rock fabrics is going to be really important, and also how to plot that orientation data. You're going to be plotting orientation of faults and veins and folds, things like that. For carbon capture, you're really going to want to think about what is the impact of faulting and fracturing on my reservoir? And can this pose a threat to any seals or fault seals? Because you want that stuff to stay in the surface. You're also going to be injecting CO2, so you want to think about induced seismicity risk and really kind of familiarize yourself with concepts of critically stressed faults and fractures. Now, when it comes to geothermal, our faults and fractures have the potential to increase reservoir permeability. So in this case, we might like them if they're at critically stressed orientations. You also want to understand what is driving faulting and fracturing and where it can be enhanced. And lastly, my last disclaimer, I can't teach you everything you need to know in 1 hour, but I can tell you a lot of what you need to know. So hopefully you've taken notes, and now you know what some of the vital concepts are for structural geology and the energy transition. And with that, I would like to thank Susan and everyone involved, as well as the AAPG. Feel free to connect with me on LinkedIn or send me an email if you have questions. And if you're curious about some of the courses we offer, reach out to us at stratigraphyhelp.com. Thank you.
Thank you. That was really wonderful. Really appreciate it. So we're looking at, what time is it? 12:58. So we have 2 minutes for questions. Actually, we can go about 5 or 10 minutes over if people would like to continue to be a part of this and really exciting and informative webinar. And let's see, I think I'm looking back at some of the questions, and one of the first ones is that, is it possible to apply the experience of geological and simulation models of oil and gas reservoirs to understand the distribution of mineral deposits? I think you answered that, but you might answer it again.
Sure, let me bring up this chat box, and I think I can see some of these questions.
Yeah.
Let's scroll back up.
And what I'd like to do is to remind everyone, if you scroll up in the chat, you will see the link if you would like to purchase the extended package. And it's only $35. You get articles worth hundreds of dollars, and also CEUs and PDHs. So you have to scroll up quite a ways, but it's just basically from Kurt Beyer asked if it's possible to apply the experience of geological and simulation models of oil and gas reservoirs to understand distribution of mineral deposits.
Yeah, I definitely think that's a possibility. It's probably one of those questions, well, it depends. But I know in a lot of the models we do, we're incorporating the geomechanics, and geomechanics is very important to mineral deposits, especially if you're looking at places where you have weaknesses, whether that's bedding plane weaknesses, or maybe a dike or a vein cutting through there. Those weaknesses can become very important. And we also want to think about things like fluid flow, even though a lot of times we're looking at fluid flow in the past of that hydraulic pathway. I feel like there could be ways to stimulate that using some of the tools from the oil and gas industry. There are, I could probably send you a great paper where they basically made a model of the subsurface and then use that to determine where the ore deposits really went, looking at some of those faults. So I think if those stimulation models involve your geomechanics as well as your structural model, I think those tools very well could go hand in hand with mineral exploration, especially in the development phase when you're thinking of your mine and where to go, deeper versus laterally. I think those could become very helpful.
And, one thing that comes to mind are Mississippi Valley type deposits.
Yes.
So, there's an example of just basically heat flow with also the structural, so that you have the hydrothermal movement, and so both enriched and caused pyrolysis as well as enrichment in, say, lead zinc area.
Yeah, I think from the mining industry, coming from oil and gas, I'm very familiar with structure and sedimentary rocks. And then moving up to the mining industry, we call them sediment-hosted metals, and many of the concepts overlap. The picture in the background that you're looking at is a sediment-hosted copper mine. And that could represent our oil and gas reservoir. That's a Wingate Jurassic Eolian age sandstone, very permeable in a lot of ways, but clearly the fractures in there are more permeable than the matrix. So that was really important for where those minerals were deposited, which in the oil and gas industry would be important for where our oil and gas reservoirs might be or where they might have flowed through.
Well, and another thing too, it's so fascinating. One might call it hydrothermal alteration if you're in mining, or you call it diagenesis if you're in oil and gas.
Yeah. Awesome. I see another question that came through. What is legal structure for injecting CO2 into subsurface? In US, mineral rights are privately owned, so you have to pay the mineral owner for rights to eternally store gas. That is not really a question I know a lot about. I would have to reach out to maybe a landman or somebody who knows more about the laws of mineral owners. Apologize, can't really answer that one.
There was a kind of housekeeping question. Somebody said, well, they clicked on the extended package and it took them to Eventbrite. Yes, that is true. I'm using Eventbrite because it's easy. So it's an easy way to be able to collect the funds for AAPG and also email everyone.
Yeah. A comment about in the Southern Canadian Rockies, most of the ore deposits predate laramide shortening, and consequently one needs to palimpsestically restore positions. That's a great comment. In that case study that I kind of threw out there, they do get into palimpsestic restorations, which is whenever you have those fold and thrust belts, a lot of times your rocks have moved laterally pretty far, several hundred kilometers in some cases. So understanding the timing of that deposit versus the fold and thrusting and where that could have moved, those palimpsestic restorations can be really helpful, which is another great structural geology concept, especially when working in fold and thrust belts or any complex geology. Those restorations can be very helpful. I'm just scrolling through the chat, looking for any other questions.
Okay, so I made a boo-boo on Eventbrite. I keep, I think, okay, I'll just make it to the end of the 1 p.m. And so then I forget that it shuts down the sales. So I'll open up another one and send that in the email to everybody that I used to follow up.
Awesome. Okay, another question. Data, where do we find in public domains mineral-related diagrams / orientations of critically stressed faults? I have a very simple answer. I like to go to Google and try Googling different words, critically stressed faults, Moore Coulomb circle, and then I click that images button and I just scroll until I find something I like and then click on that image, and then sometimes it'll give me similar images below that, and then I can click on more. So not too technical, but I kind of just end up going to Google where I'm trying to find things. And then sometimes if I click on something, it'll take me to a paper that I need to pay for. Unfortunately, there are some great resources that are public, and you kind of just have to click through there until you find something that catches your eye, and then in the description, it's kind of what you're looking for.
And you started out with a lot of great resources from the USGS and critical minerals.
Yeah, the USGS is also a great source because everything's really public. And I know that in that downloadable package that you send out for certain people who wanted that, I do have a Word document with all the links in there of everything that I showed in this presentation, just to kind of make it easy to take you where I got that from. And someone's asking, could it be possible to plan a virtual geo trip on geothermal? I would say yes. Let's go to Nevada and go check out some great structural geology over there. And then there was a question. The link to the extended package took you to the Eventbrite page. I think that is correct.
Yeah, that's my boo-boo. So don't pay attention to the expired Eventbrite page. I'll send a better link.
Okay. So this is 1 hour power geology. I agree. There's so much that I could teach you, but a lot of these things I teach are like 3-day classes or week-long classes. It's hard to teach it all in an hour. I can give you a list, but as far as teaching goes, it takes more time.
Yeah, I think it's so wonderful, and we hope that you'll teach a full day, or if you do, and teach a full day or course or 2 or 3 day, let us know when.
Awesome. Do I have any info on ore deposit exploration or indications in HT/HP regimes? I'd have to think on that one. I don't have anything off the top of my head. I probably have to do a Google search on that one. And there's a shout out to the Kansas Interdisciplinary Carbonate Consortium in the chat. And then will the video be available? I believe it will be available.
Yes, you'll receive an email with a link.
Okay.
It'll take me a day or so to process the recording.
Okay. Awesome. I think I've scrolled through the chat. If I missed anything, feel free to just shout at me.
I think it's just wonderful. And I mean, I think you're really an inspiration, Molly. I would just like to let everybody know that Molly posts Mining Mondays, and you were at LEED in North Dakota and I just loved it because I visited it two years ago. but then in the gold mine, and also in the you might tell people a little bit about your experience in the Black Hills.
Yeah, so we went out there for a few days, and I would say a year, maybe a year or so ago, I started looking at some of the major mines in the US that I wanted to visit, and Homestake was definitely at the top of the list, if not the top. You'll have to look it up on Google Earth, or maybe go to my LinkedIn page. I have a couple of videos, but it's a large mine that they dug out at the surface. But once you're in there at the building that you can go into, what tells
The
you
information center, yeah.
Yes, thank you. The information center. They've actually dug down like greater than 8,000 feet. And coming from the oil and gas industry, I'm like, okay, that's kind of what we drill a well at. That's incredibly deep, but they've dug a mine down there and they have a map of that. And then if you talk to the lady who tells you the information on there, she tells you about how hot it is at those depths. And she's got some beautiful rock samples with the gold in it. It's a great place. It's a great place to stop at. I was in the parking lot and took some drone footage. I didn't exactly get permission. I think next year when we go, I'm going to go and ask if they'll let me actually fly into the mine. I just tried to stay above the parking lot so I didn't make anybody mad or getting in too much trouble. And I didn't want to lose my drone in the mine either, because they weren't going to let me in there no matter how much I begged. But if you know any connections who can get me in there, then definitely reach out to me. I hope
I
to be
don't
back
think they do
next summer.
tours anymore. They turned it into a lab where they do neutrino experiments
Yeah,
in dark matter. And you
but it's
mentioned that
really neat.
also in your LinkedIn.
That's true. Yeah. And it's just really great to see from the surface. Just visually, I was super excited the whole time I was there. Probably a little bit obnoxious, but it's okay.
Oh, wow. Steve Jorgensen got to go down into the mine. Yeah, there's a really interesting video. It's about the Homestake mine while they were building it. It's like from the 50s or 40s. It's so incredible. It's like a documentary from the 40s or 50s, and they talk about how many trees they used to build it, and you just kind of like, wow. And just the requirements of mining.
Yeah, it's incredible. There's some good information that Ken just posted to the chat.
Yes, thank you, Ken.
And Google it and go to the Google images and you can see the great surface geology there. There's this, I always thought it was a vein system, but they kept calling it a rhyolite dike, but it's white against the really very dark rock, almost black. And it just stands out beautifully at the surface.
What's so interesting is we know that there's additional mineralization and there are a lot of little small mines in the area, but because of permitting, et cetera, it's been essentially shut down.
Yeah.
But
cool.
We're saving it for the future. I'm kind of like, have mixed emotions about mining because I feel sad when all these beautiful crystals and things are just crunched up.
I know. Structural geology is awesome when it comes to mining because you get such awesome structures, but it is a little destructive. Cool.
Well, this is wonderful. I just want to thank you again, Molly. This is really fantastic. Want to encourage everyone to renew, join, apply to be a member of AAPG and also to join the Division of Structure and Geomechanics, Petroleum Structure and Geomechanics. Molly's a vice president. And just I want to thank Linda Sternbach for who's vice president of sections again for speaking with us. And Linda, would you like to say a few final words?
No, I really enjoyed this program. It covered so much. And I really look forward. I'm going to get the extended package. So why don't you go ahead and get that extended package because it sounds like you're going to need to refer.
Perfect. Well, thank you. Thanks, everyone. I'll stop recording and we will see you later.
Awesome. Thank you, guys.